Welcome back. This is lesson 05, adding probabilities. Some key vocab before we get started. You can pause the video while you write this down. Our key terms are theoretical probability, experimental probability, compound event, and mutually exclusive. We will likely not get to compound event in this video. That will be with our next lesson in multiplying probability, 06. Okay, so first we need to talk about theoretical versus experimental probability. So theoretical probability is the left side of the screen that you're seeing. So it's the numbers that we play with in theory. Okay, so if the world were perfect and outcomes always happened the way that they were supposed to, that's the probability that this represents. Okay, and some notation to get familiar with. Let's see where my pen is. Some notation for you to get familiar with looks like this: P, and then parentheses, another letter inside. We read this as the probability of an event E. Okay, so sometimes you'll see the letter A, the letter B, but that's read as the probability of an event. Okay, and in general, we just take the number of outcomes that we want for a specific situation and divide it by the total number of possible outcomes. Okay, an experimental probability, it's a similar idea, except we are working with something that happens in real life. Okay, so for experimental probability, you'll be given data, you'll be given results from an experiment, and you'll be asked to compute the probability of that event actually happening. Okay, so we take the number of favorable trials or the number of times something happened that we want, and we divide that by the total number of possible trials. Here's our first example with theoretical probability. So a single die is rolled. What is the theoretical probability of rolling a 6? So if the world were perfect and all dice were like weighted equally, we should roll a 6 the same number of times that we roll other numbers, right? So think about a die. You can roll a 1, a 2, a 3, a 4, a 5, or a 6. And the probability that we roll a 6 is 1, because the outcome, there's one of those possibilities in this whole list out of the total number of outcomes is 6. Okay, so the theoretical probability of this event is 1 over 6. Okay, and when we talk probability, if you end up taking more statistics in the future, notation is very important. So we're going to get started off on the right foot and define our events. So we'll say this theoretical probability of rolling a 6, we'll say P of, so the probability of rolling a 6 equals 1/6. Okay? Or sometimes you might see it written out as P, and then there's more words like P over, like rolling a 6. That's another notation that you might see. Example 2, experimental probability. So now we actually did an experiment where we rolled a die many times, and the data is shown in this chart. So it's asking for the experimental probability of rolling a 6. So over here we can see that we rolled a 6 10 times. So it's going to be 10 over something. And we need to figure out how many total outcomes there were. So we'll estimate that they rolled a 5 7 times, we rolled a 4 6 times, we rolled a 3 12 times, we rolled a 2 6 times, and we rolled a 1, we'll say 9 times. Okay, and so now we need to add these up. So 12 and 10 gives us 22, plus 7 gives us 29, plus 6, 35, 41, and 50, I believe. So 10 over 50 is 1/5. So the probability of rolling a 6 equals 1/5 in this case. But in theory, it should be 1/6. So in this experiment, we rolled a 6 a bit more often than we would normally expect. Okay. Next concept after theoretical versus experimental probability is the idea of being mutually exclusive. So if two events are mutually exclusive, it means they cannot happen at the same time. I like to remember this by thinking about if you got your, your significant other, you got your boo thing. If you both agree that you are mutually exclusive, it means that you're official, you're not seeing other people, and you both are on the same page with that. Okay, you're exclusive and you're mutual about being exclusive, meaning they're not dating anybody else, so nothing else is going on. Okay, so an example in the probability world of two events that are mutually exclusive is if you think of a deck of cards, being a king or being a queen, those events are mutually exclusive because if a card is a king, it cannot be a queen. So here I have a Venn diagram to represent the possibility of being a king or being a queen. Notice that the circles are not overlapping at all because they cannot happen at the same time. So the opposite of that would be not mutually exclusive, meaning events can happen at the same time. So sticking with our card example, if a card is a king, it could be a spade. If you're not familiar with decks of cards, there are face cards like king, queen, jack. Sometimes an ace is considered a face card. And then there's 10, 9, 8, 7, 6, 5, 4, 3, 2. Okay? And then in decks of cards, there are 4 suits: spades, clubs, hearts, and diamonds. Spades and clubs are black, and diamonds and hearts are red. So the face cards and the number cards each have colors and shapes, suits associated with them. So it is possible to have a king of spades. So if we're in the probability world, thinking about the probability of a card being a king and the probability of a card being a spade, if we're calculating those two probabilities, the probability of being a king is, let's see, 4 out of 52. And the probability of being a spade is, it's a quarter of the deck, so it's 13 out of 52. But the problem is both of these probabilities, the 13 out of 52 and the 4 out of 52, they're both counting that king of spades, so it's being double counted. Okay, so to account for that, when we get to the addition rules, we're going to have to subtract out that probability once. Okay, but before I get too far, here are some formal addition rules for probability. So if two events A and B are mutually exclusive, meaning we're back here, they cannot happen at the same time. If they're mutually exclusive, then the probability that A or B will occur is just the two probabilities added together. Okay, so in this case, the probability that a card is a king or a queen is the probability that a card is a king plus the probability that a card is a queen, which would be 8 out of 52. Okay, this is an exclusive or, meaning it is either A or B, not both. Sometimes in the English language, when we say or, like, I need to get an A or a B in order to pass this class, we mean that either one's fine, both are great, but in the math world, an exclusive or means it has to be one or the other, not both. Okay? So if they're mutually exclusive, you just add their probabilities together. If they are not mutually exclusive, then we have to subtract out the and. We have to subtract out the probability that they're both going to occur. Okay? So it's similar. We're adding the probabilities together of the individual events and then subtracting out the and. So back with the card example, the probability that a card is a king is 4 out of 52, plus the probability that a card is a spade is 13 out of 52. But we need to subtract out our king of spades, which happens 1 out of 52 times. So this probability would end up being 16 out of 52. And if you choose to reduce that down, you should end up with 4 out of 13. Okay. We have a couple more examples, and then we are done. Keisha has a stack of 8 baseball cards, 5 basketball cards, and 6 hockey cards. If she selects a card at random from the stack, what is the probability that it is a baseball or a hockey card? First question, are these events mutually exclusive? So a card is either a baseball card or a hockey card. It cannot be both, because then it would be like a combo baseball hockey card, and that is not an option here. Okay, so these events are mutually exclusive, meaning we can just add the probabilities together. So sticking with proper statistical notation, we're going to define our events. So let A is going to be the event that the card is a baseball card. Baseball card. And then let B represent the event that we have a hockey card. Okay? So then the probability of A or B occurring equals those two probabilities added together. The probability of event A happening, probability that we get a baseball card, is 8 out of 19. I just added up 8 plus 5 plus 6 to get that. And then the probability that we have a hockey card is 6 out of 19. So this simplifies to 14 out of 19. For probability, we like to leave it as fractions. Decimals would also be correct, but typically we will leave it as fractions in here. Last example, suppose that of 1,400 students, 550 take Spanish, 700 take biology, and 400 take both Spanish and biology. What is the probability that a student selected at random takes Spanish or biology? So our first question is, are these events mutually exclusive? So think about school. It is possible for you to take both Spanish and biology, meaning these events are not mutually exclusive. Since they're not mutually exclusive, we're going to have to subtract out the overlapping probability. Okay? Sticking with our proper notation, let A be the event that a student takes Spanish, and let B be the event that a student takes biology. So then the probability that A or B happens is the two probabilities added together minus their overlap, minus the probability that A and B happen. Okay, so the probability that a student takes Spanish is 550 out of 1,400. The probability that a student takes biology is 700 out of 1,400. Subtracting the overlap, we need to subtract 400 out of 1,400. When we simplify this out, we should get 850 out of 1,400. Okay. We should, best practice would be to simplify this to lowest terms. Okay. I'm not going to do that right now, but in general, we should get this down to lowest terms. That should be it. Take a look at page 7 in your homework packet, and we will go over any questions you have tomorrow.